Good morning to all of you. I am Tanu from BSc Chemistry Honors second year. Now we discuss about the distribution law. Let's start. Introduction. It is observed that when a solid or a liquid is added to a mixture of two immiscible liquids, in both of which it is soluble, example iodine to a mixture of carbon disulfide and water, or succinic acid to a mixture of ether and water, it distributes itself between the two liquids in such a manner that the ratio of concentrations of the substance in the two liquids is always constant at constant temperature. These observations were made by Bartholdt and Jungfleisch in 1872. However, it was pointed out by Nast in 1891 that the ratio of the concentration is constant only when the solute has the same molecular weight in both the solvent. Hence, the generalization was put in a proper form by Nast and is called the Nast distribution law. It states as follows: a solute, that is a solid or a liquid, distributes itself between the two immiscible solvents in such a way that the ratio of the concentration of the solute in the two solvents is constant at constant temperature, independent of the presence any other molecular species, provided that the solute has the same molecular state in both the solvents. Thus, if a solute X distributes itself between the two immiscible solvents A and B, then if X remains in the same molecular state in both the solvents, we will have concentration of X in solvent A divided by concentration of X in solvent B equal to C1 by C2 equal to K, that is a constant. The constant K is called the distribution coefficient or partition coefficient. To test the validity of this law, different amounts of a solution of iodine may be added to mixtures of water and carbon tetrachloride or CS2 taken in different bottles. These are then shaken and allowed to stand. A known volume of each layer is pipetted out and then titrated against hypo solution to find out the concentration of iodine. Similar experiments may be performed with other solutes and immiscible solvents. A few results of some earlier experiment are given in the table of the next page. Conditions under which distribution law is valid. The distribution law is valid only in the following condition. First, the temperature must remain constant throughout the experiment. Second, the two solvents should be mutually immiscible. Third, the amount of solute added should be small, that is, the solution should be dilute. This is essential because in certain cases the solute added affect the mutual solubility of the solvents. Fourth, the solute must have the same molecular state in both the solvents, that is, it should not undergo association or dissociation in any of the solvent or combination with any of the solvents. Thus, the law is not valid for the distribution of benzoic acid between water and benzene because it has been observed that in benzene, benzoic acid undergo association to form dimers, that is, it exists as C6H5COOH2. Similarly, the law is not valid for the distribution of any electrolyte between water and a non-polar solvent like benzene, CS2, CCl4, etc. because the electrolytes undergo dissociation in water. These are now thermodynamic derivation of the distribution law. The thermodynamic derivation of the distribution law is based upon the principle that if there are two phases in equilibrium, that is two immiscible solvents containing the same solute dissolved in them, the chemical potential of a substance present in them must be same in both the phases. From thermodynamics, we know that the chemical potential mu of a substance is a solution given by mu is equal to mu naught plus RT ln of A, where mu naught is the standard chemical potential and A is the activity of the substance or solute in the solution. Thus, for the solute in liquid A, we have mu A is equal to mu naught A plus RT ln of A. Similarly, for the solute in liquid B, we have mu B is equal to mu naught B plus RT ln of activity of B. But as already stated, since The liquids A and B are in equilibrium, so mu A equal to mu B. Then mu naught A plus RT ln of A is equal to mu naught B plus RT ln of A for B. RT ln of A, by putting this equation we find that ln of A, activity of A divided by activity of B, is equal to mu naught B minus mu naught A by RT. Further, at a given temperature, mu naught A and mu naught B are constant for given substance in the particular solvents. Hence, at constant temperature we have from equation ln of A for A divided by activity of B is equal to constant, and therefore activity of A by activity of B is equal to constant. This is the exact expression for the distribution law. However, if the solutions are dilute, the activities are equal to the concentrations, so that the expression is modified to concentration of A by concentration of B equal to constant, which is the original form of the distribution law. Change in the molecular state and distribution law. As mentioned earlier, Nernst was the first person to point out that the distribution law in the form C1 by C2 equal to constant is applicable only if the solute remains in the same molecular state in both the solvents, that is, it does not undergo association or dissociation in any of the solvent or combination with any of the solvents. If, however, such changes take place in any of the solvents, then the law cannot be applied to the total concentration of the solute in the two phases, but only the concentration of the identical molecular species in two phases. In each of these cases, the distribution law equation is modified as discussed below for a few simple cases. Case 1. When the solute undergo association in one of the solvents. Suppose the solute X remains in the normal molecular state in the phase 1, but N molecules of it associate to form complex molecules Xn in phase 2. Then the following two equilibria will exist simultaneously. X phase 1 concentration X, second NX से X की N in the same phase 2. Suppose the total concentration of solute X in phase 1 is equal to C1 and the total concentration of solute X in phase 2 equal to C2. Also suppose alpha is the degree of dissociation of the solute in phase 2. Then concentration of associated molecules in phase 2, that is Xn is equal to 1 by N C2 alpha, and concentration of undissociated molecule in phase 2 is equal to 1 minus alpha C2. Applying the distribution law in equilibrium, we get concentration of solute X in phase 1 divided by concentration of normal molecules of X in phase 2 equal to constant. C1 divided by 1 minus alpha C2 equal to constant. Again, applying the law of chemical equilibrium to equilibrium second, we get concentration of associated molecules in phase 2 divided by concentration of normal molecule in phase 2 equal to constant. 1 by N C2 alpha divided by 1 minus alpha into C2 की power N is equal to constant. C2 alpha divided by 1 minus alpha C2 raised to power N is equal to constant, where N is a constant. Taking the nth root, we get root of N C2 alpha by 1 minus alpha C2 equal to constant. Dividing equation 1 and 2, we get C1 by under root of nth C2 into alpha is equal to constant. When the molecules in the phase 2 are almost completely associated, alpha is equal to 1, and therefore C1 by under root of C2 is equal to constant. Alternatively, the same result may be obtained in a simple manner as follows. Suppose concentration of the solute X in phase 1 is equal to C1. Concentration of the associated molecules in phase 2 equal to C2. Concentration of the simple molecules in phase 2 is equal to C3. Applying the distribution line in equilibrium 1, we get C1 by C3 equal to constant. Again, applying the law of chemical equilibrium to equilibrium 2, we get C2 by C3 raised to power N is equal to constant. Taking the nth root of both the sides, we get nth root of C2 divided by C3 is equal to constant. Now we get C1 by nth root of C2 is equal to constant, which is same as derived above. Thus, in such cases, when the solute undergoes association in one of the solvents, the constant value for the partition coefficient is obtained not for the ratio C1 by C2, but for the ratio C1 by under root nth of C2. This relationship has been confirmed by studying the distribution of benzoic acid between water and benzene, the acid existing mainly as associated molecules in benzene solution. The following results were obtained. Thus, whereas the ratio C1 by C2 shows great variation, the ratio C1 divided by under root of C2 is nearly constant. The formula C1 divided by nth root of C2 is equal to K is commonly used for finding the value of n, that is the extent of complexity of the solute molecules in one of the solvents. This is done by finding out the concentration C1 and C2 of the solute in the two solvents in a number of experiments. The value of n is then calculated as explained later in section 11.5.2. Now case second. When the solute undergo dissociation in one of the solvent, as before, suppose the solute X dissolves in the phase 1 without any change in the molecular state but undergoes dissociation into Y, Z, etc. in the phase 2. Then as shown, the following two equilibrium will be set up. X for phase 1 tends to X for phase 2. Second is X tends to Y plus Z in the same phase second. Suppose total concentration of solute X in phase 1 is C1 and total concentration of solute X in phase 2 is C2. Also, suppose the degree of dissociation of the solute in the phase second is alpha, then concentration of undissociated molecules in phase 2 is equal to 1 minus alpha C2. Applying the distribution law to equilibria, we get C1 divided by 1 minus alpha C2 is equal to K, that is constant called partition coefficient. Note, it is obvious that if the solute undergo dissociation in phase 1 with degree of dissociation is equal to alpha but remains normal in phase 2, then the formula obtained will be C1 into 1 minus alpha by C2 is equal to K. Similarly, if the solute undergoes dissociation in both the phases with degree dissociation is alpha in each, then the formula will be C1 into 1 minus alpha by C2, 1 minus alpha is equal to K. From the above expression, the degree of dissociation alpha can be calculated. Case third, when the solute undergoes combination with one of the solvents, suppose the solute X remains in the normal molecular state in phase 1, but one molecule of it combines with n molecules of the solvent S to form the compound molecules XNS in phase 2. Then, as shown in the figure, the following two equilibria will be established. X for phase 1 tends to X to phase 2, X plus NS tends to X into NS for phase second. Suppose concentration of the solute X in phase 1 is C1, concentration of normal molecules in phase 2 equal to C2, concentration of solvent molecule in phase 2 equal to CS, and concentration of compound molecule in phase second is equal to CC. Applying the distribution law to equilibrium, first we get C1 by C2 equal to K, that is the distribution coefficient. Again applying the law of chemical equilibrium to equilibrium second, we get Cc by divided by C2 into Cs raised to power n is equal to K1, that is equilibrium constant. Since the solvent in phase 2 is present in excess, its concentration Cs remains almost constant in spite of combination with the solute X, particularly if the solute is added in small quantity, that is the solution is dilute. The Cs raised to power n is constant, and so the equation becomes Cc divided by C2 is equal to K1, Cs raised to power n is equal to K2. There is another constant. Adding 1 to both the sides, we get 1 plus Cc divided by C2 is equal to 1 plus K2. C2 plus Cc divided by C2 is equal to 1 plus K2. Dividing equation 5th and 7th, we get C1 divided by C2 plus Cc is equal to K divided by 1 plus K2 equal to K3, that is another constant. But C2 plus Cc is the total concentration of the normal as well as the solvated molecules of the solute X in phase second. Thus, the above equation in fact implies that total concentration of the solute X in phase 1 divided by total concentration of the solute X in phase second is equal to constant. Hence, we conclude that when the solute enters into chemical combination with one of the solvents, there is no modification of the distribution law equation except that the numerical value of the partition constant is changed. Application of distribution law. First, in calculating the solubility of a solute in a solvent, when the two immiscible solvents are in contact with each other and the solute is added in such a large excess that saturated solution are formed, then the concentration of the solutions at this stage will be equal to their solubilities. Assuming that the distribution law is applicable for such concentrations, we will have C1 divided by C2 equal to S1 divided by S2 equal to K, where concentration C1 is equal to S1 is the solubility of the solute in solvent 1 and concentration C2 is equal to S2 is the solubility of solute in solvent 2. Thus, knowing the distribution coefficient K and the solubility of solute in one of the solvent, the another can be calculated. In studying the extent of association or dissociation of the solute in a solvent, we have already seen that when a solute undergoes association in one of the solvents in which its total concentration is C2 and has the normal molecular state in the second solvent in which its concentration is C1, the distribution law formula is modified to C1 divided by nth root of C2 is equal to K, that is the distribution coefficient. From this formula, the value of n can be calculated either by hit and trial method or by logarithmic method as explained below. First, hit and trial method. The value of C1 and C2 obtained in different experiments are put in the equation. C1 divided by nth of C2 is equal to K. Then putting n is equal to 2, 3, 4, etc. one by one, the values of K are calculated in each case. The number which gives constant value for K is the correct value for n. Second, logarithmic method. The formula of finding n is C1 divided by nth root of C2 is equal to K. C1 divided by C2 raised to 1 divided by n is equal to K. C1 is equal to C2 raised to power 1 by n into K. Taking logarithm of both sides, we get log C1 is equal to 1 by n log of C2 plus log K. For two sets of values C1, C2 and C1 prime to C2 prime, we have find that n is equal to log C2 minus log C2 prime divided by log C1 minus log C1 prime. Hence, n can be calculated. Similarly, when a solute undergoes dissociation in one of the solvents, X tends to Y plus Z in which its total concentration is C2 and has the same normal molecular state in the second solvent in which its concentration is C1. Then we have C1 divided by C2 into 1 minus alpha is equal to K, the distribution coefficient. From this formula, the degree of dissociation alpha can be easily calculated. In predicting distribution indications, it has been seen that iodine distributes itself between CS2 and water with a distribution coefficient equal to 400 towards CS2. Thus, if a weak solution of iodine is to be estimated, then a few drops of CS2 may be added to this solution. As a result, an considerable amount of I2 will pass into CS2 layer and give it a deep violet color. Now the solution may be titrated against hyposolution till the violet color in CS2 layer disappears. Thus, iodine acts as a distribution indicator in this case. In the study of chemical equilibria leading to the formation of complex ion, Ki plus I2 tends to Ki3, KBr plus Br2 tends to KBr3, CuSO4 plus 4NH3 tends to CuNH3 fourth SO4. Distribution law helps us to determine the equilibrium constant for any of the above equilibrium reactions and hence to establish the formula of complex ion on the basis of constancy in the value of the equilibrium constant. As an example, let us consider the first equilibrium reaction. To study of this following equilibrium involves the following step. First, a solution of iodine in CS2 is shaken with water to find out the distribution coefficient of iodine between water and CS2. Second, a solution of iodine in CS2 of known concentration is shaken with Ki solution also of known concentration. Third, after the distribution of iodine is complete between the two layers, the concentration of iodine left in the CS2 layer is determined by the titrating against standard hypo solution. The result is then calculated as follows. Suppose that initial concentration of iodine in CS2 is equal to A moles per liter, initial concentration of Ki solution is equal to B moles per liter, concentration of I2 left in CS2 layer after distribution is equal to C moles per liter, distribution coefficient of I2 between water and CS2 is equal to K. As iodine reacts with Ki, the total concentration of iodine in the aqueous layer is much higher. Obviously, total concentration of I2 in free and combined state in aqueous layer is equal to initial concentration of I2 in CS2 minus concentration of I2 left in CS2 layer is equal to A minus C moles per liter. Concentration of free I2 in aqueous layer can be calculated by applying distribution law. Concentration of free I2 in aqueous layer divided by concentration of I2 in CS2 layer is equal to K, but concentration of I2 in CS2 layer is equal to C moles per liter. Concentration of free I2 in aqueous layer is equal to K C moles per liter. Amount of I2 that has combined with Ki is equal to A minus C minus Kc moles per liter equal to D moles per liter C. Now according to the reaction, Ki plus I2 give rise to Ki3. Now number of moles of I2 combined equal to number of moles of Ki combined equal to number of moles Ki3 formed. Concentration of Ki3 in the aqueous layer is equal to D mole per liter. Concentration of Ki in aqueous layer is equal to B minus D mole per liter. Concentration of I2 in aqueous layer is equal to Kc mole per liter. Substituting these values in the equilibrium law expression, K prime is equal to Ki3 divided by Ki into I2. The equilibrium constant K prime can be calculated. Starting with different initial concentration of iodine and Ki solutions, the value of K prime is determined in each case. A fair constancy in the value of K prime confirms the formula of the complex or that of the complex ion. In the process of extraction. The process of extraction is of great importance both in the laboratory and industry. In the laboratory, the process is often used for the removal of dissolved substance from an aqueous solution with the help of organic solvents like ether, chloroform, carbon tetrachloride or benzene. In the industry, the process is used to remove the impurities from the product. Basically, the process involves shaking of the aqueous solution of the substance with an organic solvent which is immiscible with water but in which the substance to be extracted is soluble. After shaking, the mixture is allowed to stand. Most of the substance passes into the organic layer from which the former can be separated out by distilling of the organic solvent. However, in order that the process of extraction may be more effective and efficient, the following two conditions must be fulfilled. First, the value of distribution coefficient of the substance between water and the extracting solvent should be greater in favor of the extracting solvent. It is sometimes possible to increase the distribution coefficient artificially by making the substance less soluble in the aqueous phase. This can be done by adding substance which depress the electrolytic dissociation of the compound being extracted. Thus, suppose that an organic acid which ionizes to a certain extent in aqueous solution is to be extracted with ether. If a strong inorganic acid is added to the solution, the hydrogen ion concentration is increased and the ionization of organic acid is reduced because of common ion effect. In the solution, there will be greater amount of the undissociated acid and hence the amount extracted will be greater. Similarly, an organic base can be best extracted in the presence of a strong inorganic base. The addition of salts also usually lowers the solubility of an organic compound in water and thus increases the distribution coefficient. Second, the whole of the extracting solvent available should not be used in one lot, but it should be used in maximum number of installments. That this factor increases the efficiency of extractions can be seen as follows. Suppose x gram of the substance are present in 1 liter of the aqueous solution. Also suppose 1 liter of ether is available as an extracting solvent and that the distribution coefficient of the substance between ether and water is 2. Now if a whole of the ether is used in one lot and x gram of the amount of substance extracted into ether, then we will have concentration in ether divided by concentration in water is equal to x divided by 1000 divided by x minus x divided by 1000 equal to 2. Then x is equal to 2 by third of x is equal to 0.67x. Thus only 67% of the total amount will be extracted in this case. Again, suppose the whole of the ether is used in two installments, each of 500 cc. After a shake with first installment of 500 cc, suppose x 1 gram of the substance passes into the ether layer. Then clearly x1 divided by 500 divided by x minus x1 divided by 1000 equal to 2. X liquid is equal to 1 by 2 of x is equal to 0.5x. Thus 50% of the total amount is extracted out of the operation. Therefore the amount of substance left unextracted is equal to x minus 1 by 2x is equal to 1 by 2x. Now 1 liter of the aqueous solution containing half of x gram of the substance is shaken with the remaining 500 cc of ether. Suppose the amount extracted into ether by this operation is x2 gram. Then x2 divided by 500 both of divided by x by 2 minus x2 divided by 100 equal to 2. x2 is equal to 0.25x. That is 25% of the total substance passes into the ether layer in this operation. Therefore, total amount of the substance extracted is equal to 50 plus 25 is equal to 75%. Thus, when 1 liter of ether is used in two equal installments, the percentage extraction increases from 66.7 to 75. Similarly, it can be seen that 1 liter of ether is used in 4 equal installments. The extraction increases further to 93.75%. A general formula can be derived which gives the amount of substance left unextracted after a definite number of operations. Suppose W gram of the substance is present in V ml of the solution made in solvent A. Also suppose that V ml of the extracting solvent B is used in each time and K is the distribution coefficient of the substance between the solvent A and B. Now if W1 gram be the amount of the substance left unextracted in solvent A after the first operation, then concentration in A divided by concentration in B is equal to K. That is W1 is equal to Kv divided by mu plus Kv into W. Again, after the second operation, if W2 gram of the amount of the substance left unextracted in solvent A, so the amount extracted is W1 minus W2 gram, then W2 is equal to Kv divided by V plus Kv into Kv divided by V plus Kv into W. Then in general, after nth operation, the amount of the substance left unextracted will be Wn is equal to Kv divided by mu plus Kv raised to power n into W. In order to extraction may be most efficient, clearly Wn should be smallest possible. This can be so if the factor is as small as possible. Now in this factor the denominator V plus Kv is greater than the numerator Kv, then Kv divided by V plus Kv is less than 1. Hence the above factor will be smallest possible when n is the largest possible. So it follows that the multi-step extraction is more economical than the single-step extraction. Further, from the above equation, it may be seen that Wn can never be equal to 0, howsoever large n may be. In other words, extractions can never be complete, howsoever large number of extractions may be carried out. Otherwise also it is clear that every time the substance left distributes itself between the two solvents, some quantity, howsoever small, must be left unextracted. Note, for the purpose of numerical problems, it must be remembered that K is the distribution coefficient of the substance between the solvent A already present and the extracting solvent B if K is given for the distribution of the substance between solvent B and A. The reciprocal of this value should be used in the above equation. The principle of multi-step extraction holds good for washing the precipitates, whereby the impurities distribute between the liquid and the precipitate. Further, in Parkes process for desilverization of lead also used is made for the principle of extraction. Silver is more soluble in zinc than the lead. Zinc is immiscible with molten lead. Thus, when zinc is added to argentiferous lead, a large quantity of silver goes into the molten zinc layer, leaving little silver in the molten lead layer. Because the distribution coefficient of silver between zinc and lead is 300 at 880 degrees Celsius, zinc containing silver forms the upper layer. Thus, by repeating the process, almost total quantity of silver can be extracted from argentiferous lead. In the determination of degree of hydrolysis, let us first study some terms and expressions related to salt hydrolysis. Hydrolysis constant. The general equation for the hydrolysis of a salt Ba may be written as Ba plus H2O tends to Ha plus BOH. Applying the law of chemical equilibrium, we get Ha into BOH divided by Ba into H2O is equal to K, that is the equilibrium constant. Hence, since water is present in very large excess in the aqueous solution, its concentration may be regarded as constant, so that we have Ha into BOH divided by Ba is equal to K of H2O is equal to KH. KH is the hydrolysis constant. Hence, Ha and BOH represent the molar concentration of the free acid and the free base produced, and Ba represent the molar concentration of the unhydrolyzed salt. The above expression for the hydrolysis constant may be written in a more general way as KH is equal to free acid into free base divided by unhydrolyzed salt. Degree of hydrolysis. The degree of hydrolysis of a salt is defined as the fraction of the total salt which is hydrolyzed. For example, if in a solution of aniline hydrochloride, 90% of the salt is hydrolyzed into aniline and hydrochloric acid, the degree of hydrolysis is 0.90 or may be expressed as percentage. We are 90%. It is usually represented by the symbol H. H is equal to number of moles of the salt hydrolyzed divided by total number of moles of the salt taken. Expression for the degree of hydrolysis for solutions of different type of salts. As salts of strong acid and base do not undergo hydrolysis, therefore to talk of KH or H of such salts is meaningless. The cases of the other three types of salts are discussed below. Salts of weak acid and strong base. Representing salt by Ba as usual, the hydrolysis may be represented as follows. It is the case of anion hydrolysis. Suppose the original concentration of the salt in the solution is C moles per liter and H is its degree of hydrolysis at this concentration. Then we have A minus plus H2O tends to OH negative plus HA. Original concentration at equilibrium C 0. Molar concentration at equilibrium C into 1 minus H CH. The hydrolysis constant KH will therefore be given by KH is equal to CH का square divided by 1 minus H. If H is very small as compared to 1, we can take 1 minus H similar to 1 so that the above expression becomes H is directly proportional to under root of 1 by C. Thus, the degree of hydrolysis of a salt of weak acid and a strong base is inversely proportional to the square root of the molar concentration. Second, salt of strong acid and weak base. For such a salt Ba, the hydrolysis may be represented as Ba plus H2O tends to BOH plus HA. That it is a case of cation hydrolysis. Proceeding as the earlier case, we get the same relationship H is equal to under root of KH by C. That is, H is inversely proportional to the under root of concentration. Salt of weak acid and weak base. Third, representing the salt by Ba as before, we have Ba plus H2O give rise to BOH plus HA. It involves both anion hydrolysis as well as cation hydrolysis. In this case, we have B plus A negative plus H2O tends to BOH plus HA. Original concentration C0 concentration at equation C1 minus H C1 minus H CH. CH is equal to BOH HA divided by B plus B A minus is equal to H square divided by 1 minus H2 whole square. Here, the relationship between KH and H does not involve C. Thus, the degree of hydrolysis of such a salt is independent of the concentration of the solution. If H is very small in comparison to 1, then we take 1 minus H equal to 1. So, the equation becomes KH is equal to H ka square. H is equal to under root of KH. Determination of degree of hydrolysis by the application of distribution law. Suppose it is required to determine the degree of hydrolysis of aniline hydrochloride, which is a salt of a weak base and a strong acid. The method consists of two steps as follows. Determination of hydrolysis constant. The hydrolysis constant will therefore be given by KH is equal to free aniline into free HCl acid divided by unhydrolyzed salt. Thus, to get the value of KH, the aim is to find the molar concentration of free aniline, free HCl acid and the unhydrolyzed salt in an aqueous solution of aniline hydrochloride. This is done by shaking aqueous solution of aniline hydrochloride of known concentration with benzene. As a result, the free aniline distributes itself between the two solvents, that is water and benzene, whereas HCl acid and the unhydrolyzed salt remain in the aqueous layer only as shown in figure 5.7. A. Calculation of concentration of free aniline in the aqueous layer. For this purpose, the concentrations of aniline present in the benzene layer is found by taking a known volume of this layer, evaporating off the benzene and finding weight of aniline left. Having known the concentration of aniline in the benzene layer, that in the aqueous layer can be calculated if the distribution coefficient of aniline between water and benzene is known, which can be found by a separate experiment. B. Calculation of concentration of free HCl produced. From the hydrolysis equation, number of moles of HCl produced equal to total number of moles of aniline produced. But total amount of aniline produced is equal to amount of aniline present in the benzene layer plus amount of aniline present in the aqueous layer. Each of these amount has already been calculated in step A above. Hence, the total number of moles of aniline produced and hence the free HCl produced can be calculated. Knowing the volume of aqueous layer, the concentration of free HCl in the aqueous layer can be calculated. C. Calculation of the concentration of the unhydrolyzed salt. From the hydrolysis equation, it is clear that the number of moles of the salt hydrolyzed equal to total number of moles of the aniline produced or free HCl produced, which has already been calculated in step B above. Hence, knowing the initial number of moles of the salt taken, the number of moles of the salt left unhydrolyzed can be calculated. Further, knowing the volume of the aqueous layer, the concentration of the unhydrolyzed salt can be calculated. Second, calculation of the degree of hydrolysis. Knowing the hydrolysis constant KH, the degree of hydrolysis of a solution of aniline hydrochloride having concentration C moles per liter can be calculated from the expression H is equal to under root of KH divided by C. Summary for review. First, Nernst distribution law. A solute distributes itself between two immiscible solvents in such a way that the ratio of the concentration of the solute in the two solvents is constant at constant temperature, independent of the presence of any other molecular species, provided that the solute has the same molecular state in both the solvents. Mathematically, C1 by C2 is equal to K, cold distribution or partition coefficient. Second condition under which distribution law holds good. Temperature should remain constant. The two liquids should be immiscible. Amount of the solute added should be small. The solute should not undergo dissociation or association in any of the solvent or combination with any of the solvents. Third, thermodynamic derivation of distribution law. The chemical potential of the solute in the two liquid A and B is given by mu A is equal to mu naught A plus RT ln of activity of A, and mu B is equal to mu naught B RT ln of AB. At equation mu A is equal to mu B, hence mu naught A plus RT ln of A equal to mu naught B plus RT ln of B. Then ln of A for A and divided by A for B is equal to mu naught B minus mu naught A by RT is equal to constant at constant temperature. Hence concentration of A divided by concentration of B is equal to constant. Then now fourth, change in the molecular state and distribution law. When the solute undergoes associations in one of the solvent, suppose the solvent 1, the solute remains in normal molecular state, but in solvent 2 we have nx tends to xn. The formula is modified to the form C1 divided by under root nth of C2 is equal to constant if the solute form dimers, example benzoic acid or acetic acid in benzene, n is equal to 2, hence C1 divided by under root of C2 is equal to constant. Second, when the solute undergoes dissociation in one of the solvent. Example, suppose in solvent 1 the solute remains in the same molecular state, but in solvent 2 we have x tends to y plus z. If degree of dissociation is alpha, the formula is modified to the form C1 divided by 1 minus alpha into C2 is equal to constant. Third, when the solute undergoes combination with one of the solvents. Suppose in solvent 1 the solute remains in the same molecular state, but in solvent 2 we have x plus ns tends to x into ns, then the formula is found to be C1 divided by C2 plus Cc is equal to K, that is concentration of solute X in phase 1 divided by total concentration of solute in phase 2 is equal to K. Thus there is no modification of the distribution law equation except that the numerical value of partition coefficient changes. Fifth, application of distribution law. First, in calculating the solubility of a solute in a solvent, if sufficient solute is added so that solutions are saturated, we have C1 by C2 is equal to S1 by S2 is equal to K. Knowing the partition coefficient K and solubility in one of the solvent, that in the other can be calculated. Second, in studying the extent of association or dissociation of the solute in the solvent. For association, C1 divided by N of C2 is equal to K. First by iterative trial method, second by logarithmic method. Third, in studying chemical equilibria forming complex ions. Ki is equal plus I2 tends to Ki3 or CuSO4 plus 4NH3 tends to CuNH3 4 into SO4. To study first equilibrium, a solution of I2 in CS2 is shaken with Ki solution. I2 left in CS2 layer is determined. Knowing distribution coefficient between water and CS2, concentration of Ki, I2 and Ki3 at equilibrium can be calculated. Substituting the values in the expression, K prime is equal at equilibrium constant lambda can be calculated. Starting with a different concentration, K prime is calculated in each case. A constancy in the value of K prime confirms the existence of equilibrium. Fourth, in the process of extraction. For the extraction of a compound present in solvent IA, the solvent called extracting solvent is added, which is immiscible with solvent A, and distribution coefficient of the compound is more in favor of extracting. If W gram of the compound is present in V ml of the solvent A and the total extracting solvent is used in n equal installments, each of volume V ml and K is the distribution coefficient of the compound between the original solvent A and the extracting solvent B, then the amount of solute left unextracted after n installment is given by Wn is equal to Kb divided by mu plus Kb raised to power n into W. As therefore greater the value of n, less is the value of Wn and more is the solute extracted. Thus, multi-step extraction is more economical than single-step extraction. Further, Wn cannot be zero, howsoever large n may be. Thus, extraction can never be 100%. This method is used in Prague's process for desilverization of lead by adding molten zinc. Fifth, in the determination of degree of hydrolysis. For the hydrolysis of salt Ba is called hydrolysis is equal to Kh is hydrolysis constant, that is Kh is equal to free acid into free base divided by unhydrolyzed salt, and degree of hydrolysis H is equal to number of moles of salt hydrolyzed divided by total number of moles of the salt taken. For the salt of a strong acid and a weak base, or a weak acid and a strong base, H is equal to under root of Kh by C, where C is the concentration of salt solution. To determine the degree of hydrolysis of aniline hydrochloride at concentration C moles per liter, the solution is shaken with benzene. Aniline distributes itself between the aqueous layer and benzene layer. Finding the concentration in benzene layer that in the aqueous layer can be calculated. This gives also unhydrolyzed salt equal to salt initial minus salt hydrolyzed. Knowing these concentration Kh can be calculated. Further, knowing initial concentration Ch can be calculated as H is equal to under root of Kh by C. Thank you.